Okay, so let's start our lecture today. Okay. Okay, so yeah. So shoot. Okay, so I think last time uh, yeah, sorry. Last time I think I solved very abruptly. Okay, so okay, so. Mm, Okay, so I think last time I was about to finish to show that this X is connected, locally semi-connected, and locally compact. Okay, so yeah, I'll leave the rest detail for you to check for the detail. Okay, so now I will continue with my proof. Okay, okay, so. Yeah, so basically we have created the space X, okay, and then we have shown that this X is Hausdorff, and then we also show that this covering projection map gamma is surjective local homomorphism, and then this space X is connected locally semi-connected and locally compact. Okay, so now so. Yeah, so remember that for part A, yeah, so for part A of the original theorem, we are trying to show that the quotient space X is connected locally, semi-connected, locally compact Hausdorff, and this gamma from this X tilde to X is the recurring space. Okay, so we have shown that this gamma is a covering map, right? Yes, and then we have already shown that this X tilde is given that yeah, this X tilde given is a simply connected locally. It's a simply connected space, so therefore it is universal covering. Okay, so then and then we also yeah, so here the only thing left is to show that this gamma is equal to the so this. Yeah, remember that this gamma is a subgroup of the group of self-homomorphism of this X tilde that acts properly discontinuously and freely on this X tilde. So we are left to show that this subgroup gamma is actually equal to the Dirac transformation group of this like vertical gamma. Okay, I'll call this the vertical gamma. To distinguish and then the other gamma is just this gamma. Okay, in order to distinguish these two. Okay. Okay, so now let me just continue. Okay, so so for the proof of B. Okay, so for the proof that this gamma is equal to the Dirac transformation group of this vertical gamma. Okay, so let's first write down the sentence for the proof that this gamma is equal to the Dirac transformation group of the of this current projection. Okay, and okay, and then okay, so okay, so let us so we fix a point x now in this x tilde. Okay, so fix the point x naught and x tilde, and then let this yeah, x naught is a point upstairs, and then we let this this x naught tilde, okay, my bad, this x naught tilde is point upstairs, and then we let this x naught, okay, to be the current projection, okay, and let this x naught to be given as this vertical gamma, the current projection of this x naught tilde. Okay. So okay, yeah. So you can think about this is like x naught tilde, x tilde, and then project it down to this x naught to this x, and then okay. So given the element phi in this gamma. So given an element phi in this dash transformation in this gamma, okay. Okay, so we have that so this vertical gamma composed with this phi is equal to gamma. Okay, let's see why it is true. So so basically if you pick any, let's see, so this phi, we know that this phi is in this group, right? Yeah, and then we know that this x tilde is, so basically the idea is that when you quotient out this phi x, right? Because this phi is in this group gamma, so it's actually in the same homotopy class. Sorry, not homotopy, but it's in the same equivalence class of this original point under this action by gamma. So therefore, they project down to the same space. Okay, and then okay, so where am I? So and therefore, yeah. So and therefore, so this implies that this because this gamma is a group of self-homomorphism, right? So yeah. So this gamma is a subgroup, or yeah, I think that it's a subgroup of the group of self-homomorphism. So therefore, and so therefore this phi, okay, therefore we know that this phi is because it satisfies this property, so we know that it is dash transformation. It is in dash transformation group. Okay. So this implies that okay, and therefore we have this phi is in this deck transformation group of this vertical gamma. Okay, so so conversely, if this phi is in this deck transformation group of this gamma, vertical gamma, then okay, so then we have that then we have the relation is the gamma of phi of x naught tilde, which is equal to this variable gamma of this x naught tilde. Okay, so this is true by definition of this depth transformation group. Okay, so and then okay, so and hence, okay. Okay, so because they are in the same equivalence class under the group action by gamma, so therefore these two are related by the group action gamma. So hence there exists a element. So there exists element. Let's say psi.
Sorry.
Oh yeah. Let's say psi in this gamma with a subset of the depth transformation group of this variable gamma. Yeah, so we show that this yeah, so we show that this we have shown this inclusion here. Okay, we have shown this inclusion here. So yeah, so with so these two things, these two are related to each other. So therefore, this implies that this phi of x is equal to this psi of x, so psi. Okay, so with phi of x, sorry, x tilde. This is what I mean. X not tilde. Sorry, yeah, it's equal to So remember, you can always take like the inverse for the equation. Yeah. Okay, so then, so therefore, by theorem 10.4.2, so what is, let me check. Okay, so this phi is so remember for theorem 10.4.2 we have the part E, right? So part E says any element in this deck transformation group take away the identity has no fixed point. Okay, so so this implies that this is the identity, right? So this implies that wait, hold on 1 second. Okay, so this implies that, so if you take the phi inverse, right, compose with phi of this x tilde is, so I think, so this implies that this is actually the identity map. Okay, by the part E of this theorem, and then okay, so this implies that they are the same thing. Okay, so why they are the same thing? Basically, you just compose with the phi on the left hand side, right? Yes. Okay. Okay. Okay, so this shows that this phi is actually in this gamma. Okay, because they're the same thing. Okay. So so I think this concludes the it concludes the result that this gamma is equal to the depth transformation proof of this vertical gamma. So yeah, so that's finished the proof of part A. So okay, so let's start with the proof of part B. Okay, so for part B, what we have is that okay, so let me state part B first. So for part B, okay, so we introduce another group called this gamma hat. Okay, so if we have this gamma hat, it's a subgroup of gamma. Oh, sorry. Subgroup of gamma. Then we have a commutative diagram. We have a commutative diagram. Okay, so let me draw the diagram. This is x tilde, this is gamma, this is x, and then here is the, okay, so here is x hat, which is being defined as this gamma hat model x tilde. So this is the equilibration of this x tilde quotient by the equilibration by this gamma hat. Okay, and then this is the gamma of gamma hat. Okay, that to be determined. Okay. 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 So I think what. Okay. So this is what I mean here is that. So this is another space, right? So we take so this gamma hat is a subgroup of this gamma. So when we quotient out by this space, this is another space, and then let this be the corresponding covering map. Okay. Okay. So yeah, and then this is the map of yeah. So this is the gamma hat. Vertical gamma hat. I think this. Okay, so this gamma hat basically is if you have this element. So the element in this S hat is basically the equivalence class of this x tilde, right? Modeled by the equation of model the equilibration of this gamma hat. So for the same equilibration, right? So you can also map them to the corresponding equivalence class in this X, right? Because if they are related by this, because this is a subgroup of this gamma, right? So if every element is related by this gamma hat, then it's also related by this gamma, right? So you can simply project them into the space X. Okay. So of covering maps. So moreover, if this x naught tilde is in this x tilde, and x naught is equal to, okay, so we fix a point in this x. We fix a point x naught tilde in this x tilde. Okay, so in this space, and then x naught equal to the projection by this vertical gamma of this x naught tilde, and this we have the x naught hat to be this projection. Okay, to be the vertical vertical gamma of this gamma, this group gamma hat. Okay, call this group gamma hat of this x naught tutor. And then we let this chi. Okay, so this is chi. Okay, this is different from x. Okay, this chi from this gamma, which is equal to the dash transformation group of this gamma, vertical gamma, the group gamma, which is to this pi 1 of this x naught. And we have this chi hat. Yeah, maybe I think it's more proper for me to use. I'm not sure what exactly you present. So I think it's better to write this. Okay. Maybe I'll figure out later. So from this group gamma hat, which is equal to the deck transformation of this gamma subscript, the covering projection of this one, with respect to this gamma, the gamma hat, the group gamma hat, and then 2 pi 1. Okay, so 2 pi 1 of x hat, x naught hat. Okay. Okay, so in other words, okay, so basically we define this. So basically we define this x naught to be that. Okay, and then we define so basically you pick a point. So I'll just write it here. So you pick a point, let's say x naught 2 like here, and then what you do is that you project it down, right? You project it down along gamma to this x naught, and then this is the projection along this one. Okay, so so maybe a point here, and then so this chi is what? This chi is from this gamma, this group gamma. Okay, so this is the dash transformation group of this gamma. Basically, this is the automorphism group of this x tilde, and then to this pi 1 of x1 x naught. Okay, so pi 1 of x naught is what? Pi 1. So pi 1 of x. Okay, so this is pi 1 of this one. Okay, so let's see. Always different. Okay. Oh, sorry. I think I didn't finish. Okay. So what I'm trying to say is that what exactly these two maps? Okay. So these two maps are so the map chi and chi hat are exactly the corresponding group isomorphisms. And then then we have that this chi composed with chi hat inverse is equal to this gamma hat star from this pi 1 of x hat x naught hat to the space pi 1 of x naught. Sorry, I mean x naught hat. Okay. So in other words, the action of this. Okay, so the action of this small r hat, the equivalent, the coequivalent class of this r hat is pi 1 of x hat, x naught hat. Yeah, based at pi 1 of x hat based at x naught hat on this x tilde is the same as that of the vertical gamma hat push forward of this r hat which is equal to this the group of this gamma vertical gamma hat of this small r hat, which is lies inside pi 1 of x naught. Okay, so this is a theorem. Okay, so basically it says are the corresponding group isomorphisms. Okay, I think what's going on here is that so remember we proved in the previous I think in the first theorem we proved, right? So there is a sorry, let me so there is such isomorphism between the Deck transformation group and this homotopy group, right? So so these are the corresponding group isomorphisms, and then we are claiming that when this chi x hat inverse when this x component chi x hat inverse, so this is equal to the this is equal to the push forward map of this. It is equal to the induced group homomorphism of this vertical gamma hat. Yes. Okay. Okay. So in other words, the action of this on this x is the same as that of the action of is the same as that of the action of so I'm not so familiar with this one. Okay, so yeah. Okay, so let me try to prove this one. The action of action. Okay, so let's first try to prove that. now leave the statement for part B. So, okay, so, okay, so for the proof of, okay, so now, okay, so suppose this gamma hat is, okay, so proof, okay, so, okay, so suppose, okay, so suppose this, wait, okay, so the surjective mapping, okay, so first, so first, okay, so this is surjective mapping, so vertical gamma hat from this x hat to x, given by this vertical gamma of, okay, of, of this small, this gamma, like gamma hat of this x to this gamma x, is well defined. It's well defined. And therefore continuous with respect to the quotient topology. Okay. Therefore continuous with respect to the quotient topology. Okay, so why it is well defined? So it is well defined because I think as I mentioned here, right? So this okay, so if you take any element x, wait. Okay, so you are taking the okay. Okay, so you are taking the okay, so here you are taking the element of this because so these are like the equivalence class of this x under the group action of gamma of this gamma gamma hat, right? So if you so basically so if you this is the equivalent relation, right? So this is the equivalence relation of this x, and then you map it into the equivalent relation of this gamma x. Okay. So this is well defined, right? And we have checked that, and then therefore continuous with respect to the quotient topology. Okay, so why it is continuous with respect to the quotient topology? Okay, so we know that this is a continuous map, right? And then what is this map? Okay, wait. So continuous with respect to the quotient topology. Hold on 1 second. So continuous with respect to the quotient topology. Okay, so okay, so continuous with respect to quotient topology. Okay, so let me maybe let's so for the quotient topology, so this gamma is definitely continuous, right? This gamma is continuous, and then okay, and then this gamma, this gamma with respect to the group action gamma hat is also continuous with respect to the quotient topology. So okay, so the continuous maps are what? Are the you can take you have an open set. Okay, so if you have an open set of x hat, okay, then yeah. Okay. So let's check why is continuous. So if you take an open set, right? So if you take an open set of this x, and then what is gamma inverse of x? What is gamma inverse of x? So sorry, what is gamma hat inverse of x? Gamma hat inverse of x is you take it is set of all. Okay. So let's check that. So then okay, so what is gamma hat inverse u? So okay, so what is gamma hat inverse u? So so this okay. Okay, so we want to show that this gamma hat inverse u is open in this x hat, right? So why it is why it is open? It is open in the quotient topology. So open means that okay. So it is open if and only if this okay. So this is open if this okay. Okay, so So this is open if we take this gamma of this group action by gamma hat inverse of this set. It's open in this X tilde, right? So let's see whether this is open in this X tilde. So okay, so I want to show that so this gamma of gamma hat, the inverse of this map is open in this X tilde. Okay, so what is this set? So okay, so why it is open in okay, so let me draw a picture here. So here, so this is U, right? Neighborhood here. So this, you think of this U as a equivalence class. Then you do the gamma inverse. That becomes a that becomes some equivalence relation. Oh yeah, sorry, yeah, some upstairs, but it may not be because this U is not necessarily open color, right? So yeah, it may not be the disjoint union, but you think of that. Yeah, you can think of this one as maybe some set. Okay, some step upstairs. Okay, and then when you okay, so yeah, so this is like this is the equation, and then this is like the points, and then okay, so this is like wait okay, so I'm trying to picture what is this gamma hat inverse of U? So gamma hat inverse U is what? So gamma hat inverse U